This is a chi-squared test for homogeneity. We're going to go through how to do this thing mostly by hand. This is testing to see if the distributions look the same. Homogeneity means same distribution. The math for a chi-squared test for independence is identical to this. The only thing that would change is your null and alternative hypothesis. For a test for independence, the null hypothesis is that there's no relationship between the variables, and your alternative hypothesis will be that there is a relationship. This is pretty similar to what's going on for homogeneity. The null hypothesis for this problem is that the opinion of the school mascot Poppy is the same for each program. And the alternative hypothesis is that each of these are not the same, that there's at least one difference. I'm comparing counted data, so I'm using chi-squared when I'm looking at any sort of categorical information like this. So my variables love, hate, and who is Poppy, those are word-based data things. That's what makes this categorical. I can count it. My chi-squared model adds, that's what this symbol means, add, your observed value minus the expected value squared divided by the expected value. It's going to tell me roughly how much error there is. So suppose this is what I observed for the love, hate, who is Poppy for those disciplines. We want to figure out what we were expecting for each of those things. Notice how my totals on the outside stay the same. It's really just the inside numbers that are going to vary. And I also need a degree of freedom. My degree of freedom will be the number of things that I have to find in order to fill in this whole grid using some sort of multiplication trick. So I'll show you what I mean by that, but I'm going to give you a formula for degree of freedom as well. To come up with the expected, I have to maintain the same ratios throughout. So if the ratios look the same throughout this whole thing, then the proportion of people that are in this math love Poppy area, while the math group appears to be 200 out of 1,000, so 20% of the group. So I should see 20% of the love Poppy show up here. So what I'm going to do is I'm going to take the total for the row divided by the total overall. So that's just 200 over 1,000. This is that 20% ratio. And I'm going to multiply this by the total of this column, 100. So intuitively, I have 20% of 100. I feel like this number should be 20, but let's just use a formula and see what we get. My row total, 200. My column total, 100. My overall total, 1,000. So here's sort of my visual trick for doing this. I go down and out, and I multiply those numbers, and then I divide it by the overall total that I have on the outside. So typing this into my calculator, I do get 20. That's looking pretty good. Let's do another one of these expected values. I'm going to do it for the hate, Poppy, and math group. This should still be 20% of this 300. So I'm thinking this should be like 60. But let's use the formula. Expected, I'm going to take the total of the row where this lives and the total of the column where it lives. So I just go out. I multiply these numbers. And I'm going to divide it by the overall total. So I'm doing row times column over the overall total. I have 200 times 300 divided by 1,000. When I type this into my calculator, I again get 60, as it kind of looked like it should be. I'm going to use multiplication trick to come up with another one or two of these things. Let's look at this art value. This is in the 300 row, so I have 300. This is in the 100 column. And my grand total is 1,000. This gives me 30. I could very well end up with decimals here because it's the expected. So this is kind of like a running average for each of these categories. If I end up with a decimal, I don't round them to the nearest whole number. I just keep them as is. So for example, nope, that still gives me a nice number. So here, this is in the 300 row and the 300 column. Divided by the 1,000, this gave me a 90 here. I've used a multiplication trick for these four values, but let's see if I can get lazy and find the remaining ones just using addition and subtraction. So if I know the first two columns, then 20 plus 60, I'm at 80. I need 120 more to get 200. I have 30 and 90, I'm at 120. 120 and 180 gets me to 300. You could still use a multiplication trick if you like that thing. 20 plus 30 gives me 50. 50 plus 50. So if I know all but one of the rows, I can solve for that last row. If I know all but one of the columns, I can solve for that last column. 60, 90, I'm at 150. I need 150 more. If you do this correctly, the last number should work both vertically and horizontally. I'm at 200, so I need 300 more to hit 500. Adding these up vertically, I get 600. My totals work out just fine. So I could solve for the outside row and the outside column. So I needed to know this 2 by 2 grid first. So I needed to know 4 values as my degree of freedom there. In general, my formula is going to look like the following. Number of rows minus 1, because I can solve for that bottom row, times number of columns minus 1. So in this case, my starting data grid that I'm trying to fill in, this 3 by 3 grid, 3 minus 1 gives me 2 for the rows, 3 minus 1 gives me 2 for the column, and 2 by 2 gives me 4. My formula matches up with what I'm seeing in the picture. I needed to know 4 of the boxes. This thing is labor intensive, but the math is going to be identical to what it looked like for chi-squared goodness of fit now. I'm going to compare all of these observed values to the expected ones. So here I have my observed table. They told me what should happen. Here I have my expected. This is what it would look like if all of the proportions were the same throughout. So I'm going to match things up, and I like to kind of cross them out as I go along just to make sure I don't miss anything. My first observed value is this top left number, 20, and that's paired up with the same top left number in this expected. So I have 20 minus 20 squared. The expected for this was 20. Next value, 80. 80 is paired up with the expected of 60. So I have 80 minus 60 squared. My expected is 60. Plus, I'm going to set up one more of these, and then I would encourage you to pause the video and then see if you could set up the remaining 6, because I'm only doing 3 of the 9 here. 100. 100 is paired up with the same spot on the other one, 120. Squared, the expected is 120, plus dot, dot, dot. So the next one, I would have 40 minus 30 squared over 30, 60 minus 90 squared over 90, 200 minus 180 squared over 180. I would have 40 minus 50 squared over 50, 160 minus 150 squared over 150, and 300 minus 300 squared over 300. If you use those outside numbers, you're not supposed to use those numbers, but just in case you tried to, your formula is pretty forgiving in that if you did 200 minus 200, you would end up getting 0. So even if you included these totals on the outside, it's not going to screw up your chi-squared value. I'm going to type this into my calculator and see what I get. And it looks like I get a chi-squared of 28.2 repeating. Chi-squared is always a right-tailed test. So when I want to look up this value, I'm going to have chi-squared CDF. Whatever my chi-squared number is, up to infinity, it's a right-tailed test varying this much or more. And then I'll have my degree of freedom. So for example, I have a chi-squared CDF of 28.2 repeating for this problem, comma infinity, comma, my degree of freedom was 4. If I am inside a TI-84, I find this by doing second vars. So second vars, chi-squared CDF, 28.22 repeating. High value is infinity, so I'm just typing in a whole bunch of 9s. Degree of freedom, 4. And I get, this is scientific notation, so this means move the decimal 5 spots over. So I move it 1 over and then 4 more zeros before that. So I would have 0.00001. This is a really small p-value. This is so small that I might even call this 0 plus kind of small, although it's not unheard of. TI-89, I'm going into stat list editor. So I'm going apps, stat list editor. I'm choosing the option for distribution, that's F5. And I'm choosing chi-squared CDF. I type in my low value, that's this 28.22 test statistic number. My upper value is infinity, so I can hit diamond catalog to get infinity to show up. My degree of freedom was 4. When I type this into my calculator, this gives me this 0.0001 number that I was talking about. That's a really, really small p-value. If I'm trying to do the same thing inside of GeoGebra, I open up GeoGebra, I go into probability, I'm already in probability here, and I choose the option for chi-squared. I type in my degree of freedom, I type in my chi-squared value, and then I want to make sure that I'm choosing the option that's shaded to the right. I don't see anything on my curve because this is so large that it's like way, way out there. So this is what's causing me to have this really small p-value. GeoGebra just calls this thing 0. It's not technically 0, it's a little bit bigger. It's this 0.00001 number, but it's still really, really small. Now that I have my p-value, I'm at that conclusion step. Reminder of this conclusion step, if your p-value is low, your null must go. This is a really small p-value. So I'm going to reject the null hypothesis, which tells me I have evidence that the opinion on the school mascot of Poppy varies by discipline. So first step, I had my hypotheses. Second step, I had my model. Third step, p-value. Fourth step, conclusion. I calculate my chi-squared value by doing observed minus expected squared over expected. I look up the p-value by doing chi-squared CDF, whatever number I get through that process, comma infinity, comma my degree of freedom. And I find these expected values by taking the total of the row times the total of the column divided by the overall total. Once you get the hang of these things, even though they're labor intensive, you kind of get in a groove, and it makes these almost, I think it's almost a soothing process because it's just repetitive button pushing, that not a lot of thinking, just some time to sort of relax while you're doing a problem. Obviously, your opinion on that might be different, but all the same, this is how you go through and you do it by hand.